Thank you very much, Danielle, for this very thorough introduction of mine, presenting my career history so nicely. So indeed, I do have a talk that's entitled Updates from the Cosmic Dawn. It's a very general talk. It's going to touch upon many different themes. As Daniel said, we're talking very much about the properties of the first galaxies here. So I'm looking at what the conditions in the first star-forming objects that turned on in the universe are. That's the first part up here. We'll talk also about the occupation of these galaxies with supermassive black holes and the AGN phenomena and what that may have done to galaxies and the intergalactic medium in the second part. And at the end of this talk, if I get around to it, and I very much hope I do, I want to talk a bit for 10 minutes about the impact that these first galaxies would have had on the intergalactic medium and how we can actually watch that process evolve. Of course, this is scientific research and nothing happens in a vacuum. These are just some of my many collaborators that have contributed to this work over the years and over the last few years, or using stuff from their materials that have come into this talk. So I was trying to figure out over the last few days how many times I've been to this institute, and it's probably somewhere between 30, 40 times I've visited the IAP over the last 20-something years to work with my friends Akim and Danielle, and I say thank you very much for this invitation to come here again. I've been to many institutes in the last couple of decades, and it feels a bit like, IAP is in a way a little bit my second academic home. So galaxy formation is what we're going to focus on. Galaxy formation is something that happens, of course, over 13.5 billion years of our cosmic time. This is my galaxy formation on one slide. It's, of course, something that happens, so long. So there's so much physics that comes in here. It happens so much in the nonlinear regimes. The way we really understand galaxy formation is with one of these. Through the realm of computer simulation. So I do primarily observations. I will only talk really about observations in this talk. One thing that I don't do is theory. So this slide is not for me. It's not about me. But if you just think about the elements that go into our theory of galaxy formation, you start at the top, redshifts beyond 100, probably when the first population of galaxies had not yet formed. We need to begin with some kind of cosmological framework of which we have some reasonable idea, but really could be far from complete. We need a theory of gravity, which is probably okay, right? But on top of this, we have to understand how the gas behaves in galaxies in a field that we generally refer to as hydrodynamics, how this couples with, or how that gas then goes on to form stars, and the first generations of black holes that turned on in our universe. And then we need a good picture of how these things grew and how the stellar populations and black holes created more material, built up their mass as cosmic time goes on. Under a broad family of processes, energy, radiation, momentum is dumped back into the ISM in a family of processes that we generally refer to as feedback. At some point, the universe was reionized, and so during this point, then radiation can propagate between galaxies. Galaxies can begin to communicate with each other and influence the way they behave or the subsequent behavior through radiative feedback. We need models of stellar evolution, radiative transfer. And if you put all this together inside of a machine like this, crank the handle, what comes out, you rearrange your punch cards at the end, make sure everything is okay. You end up with models of the universe that look like this. So defining the structure, the chemistry, the abundances. Couple this with radiative transfer, you can actually make mock observations of the universe. These have reached such a point, in fact, some time ago, that if you convolve your data output, your radiative transfer output with the telescope, add appropriate noise and give mock observations to observers in most parameter space, they are unable to tell you the difference between an observed observation and a theoretical model. And to me, this is really a triumph for physics, an underappreciated triumph for physics that really includes the work of thousands of people over the years. And this is where my observational efforts come in. These are the things that I'm really interested in: star formation and black hole formation, reionization, stellar feedback, and chemical enrichment. I'll talk about a handful of things today. So I'll just sort of put in context why the black hole formation aspects are important. Black holes live in the central regions of basically every massive galaxy and probably a large number of dwarf galaxies as well. They're very difficult to observe. They influence their environment from scales, even down to the black hole in the first few parsecs from the supermassive black hole. They drive out winds over scales of tens of kiloparsecs, and some of the jets from black hole accretion, or as a result of black hole accretion, reach megaparsec outside of galaxies, influence the whole central regions of galaxy clusters. So energy is deposited over basically all of these scales. So they're really important for the way galaxies will continue to form, or the gas behavior inside of the galaxies. There are very tight scaling relations between the observed properties of black holes and the galaxies. These manifest as mass and velocity dispersion, stellar mass. There's a tight coupling between black hole formation and star formation. That's visible in the accretion history of black holes in our universe. It really does track the star formation rate density almost in lockstep for reasons, again, that aren't completely understood. Now, also in the last few years, we've been able to identify AGN activity as far back as redshift 10 or so. And that's a time when the universe was probably 90% neutral. And if these things are really as ionizing as we expect them to be, it could be that AGN have also played a significant role in reionization, although this is really quite uncertain. So this is a model of how the universe was reionized. It's a simulation from the Thiessen team. What you see on the left is the ionization state of the universe. I'd just like to stop this if I can. And I always mess it up when I try and stop it. No, that worked. Okay. So what you see on the right-hand side of this figure is the regions of the universe where radiation is flooded into it. So the universe is forming galaxies. These galaxies are producing radiation. That radiation is shown by the orange light on this side. And what you see here is the neutral and ionized gas distribution of the intergalactic medium, where the neutral regions are in red, so the universe is mostly neutral, and the ionized bubbles are coming up in blue. And as this video goes on, I hope I don't mess it up. No, I don't. It goes on, and when we see these redshift 9 galaxies, they're embedded mostly in the neutral universe, in these bubbles that are continuing to grow. And you see here that the radiation is sort of flooding between galaxies. It's not going everywhere in the universe. There's no sort of universal background yet. And as we reach redshifts of 6, the universe is basically done with the ionization process, and we have a smoothish, homogeneous-ish ionizing background. There's one little neutral island left there at redshift 5. These are a picture of the reionization history. And of course, we need to understand reionization because it's the first time at which galaxies could communicate ionizing radiation between each other. This evaporates the gas off small galaxy halos, quenches galaxy formation, and leaves an imprint in the local distribution of dwarf galaxies, something that we can see in the, even down as far as the local group, perhaps. And also, when the universe finally does become ionized, it's flooded with free electrons, and this Thomson scattering shapes the cosmic microwave background. So there's all kinds of reasons why we have to get all of these things right if we want to properly understand the process of galaxy formation. This was all good. We had a great time working on this for my entire career. And then 3 years ago, something strange happened. 9th of August 2002, the Shiny Gold Space Telescope opened its eyes for the first time. These are images not from that date, but from before the telescope was launched. And this telescope has really, in those 2 years, transformed the field of observational astronomy, particularly at the highest redshifts. There were many surprises that came in the first couple of years. Probably you've heard about them all, or some of them. I'm just going to go over them now. The first thing I'd like to highlight is the fact that when we just had Hubble Space Telescope and big telescopes estimating the number of bright galaxies that there are at higher redshifts, the number density of galaxies was decreasing with increasing look-back time as the universe became younger and younger. And some of the first galaxy surveys from JWST were finding at redshifts 12, 13, 14, there's an overabundance of bright galaxies that amounts to a factor of approximately 5. Many more bright galaxies than we would have expected. Not only are there bright galaxies, but some of them are not even particularly young, even though the universe is. If you look at the spectra of some of these objects, they show spectral features of Balmer absorption and a Balmer break there that are consistent with star formation that's already been turned off for order of 100 million years or so. So not only are the galaxies there in place very early, but they're also They must have formed very early indeed. If you look at the number densities of black holes in these galaxies, or AGN in these galaxies, these are the sort of quasar predictions and extrapolation. This is number density against magnitude. And you see that the JWST data are also coming in factors of whatever, depending on which lines you prefer, 3, 5, 10, 20, maybe more abundant than the pre-JWST estimates would have given us. Not only are the black holes there, but if you look at conventional or typical black hole mass scaling relationships, sort of black hole mass against stellar mass over here, some of these newly identified AGN were also overmassive in their black holes compared to the stellar populations. High redshifts telling us that this black hole formation would have gotten busy very early, but also the growth has probably been very, very rapid. And finally, we can measure the abundance patterns in some of these early galaxies. Particularly as we've been given access to these strong ultraviolet lines of carbon, nitrogen, and oxygen. And we can see that in a handful of these early galaxies, they are displaying abundance patterns that are very inconsistent with those that we see in the more modern universe. This is just nitrogen, oxygen abundance, and they're sitting up here while all of our local galaxies tend to follow a relationship down here. So these were some of the first surprises about the galaxies. There's also surprises in the intergalactic medium behavior, because we've been doing for a long time Lyman alpha observations, as Daniel said in his introduction. This is the strongest recombination line in the spectrum of a star-forming galaxy, Lyman alpha in the UV. And Lyman alpha is very interesting and important because it's the ground state resonance line of atomic hydrogen. So it's produced by the n equals 2 to 1 electronic decay, but it's also absorbed in that same transition. And most of the hydrogen, when it's neutral, all the hydrogen when it's neutral, it's going to be sitting in that ground state, producing material that's very optically thin to Lyman alpha. So when you put galaxies, Lyman alpha emitting galaxies, in a neutral universe, you expect that Lyman alpha not to be reaching our telescopes, but to be absorbed basically in the intergalactic medium at high redshift, producing a drop. So this is the fraction of galaxies that emit Lyman alpha as you go out in redshifts, and we saw always a drop beyond redshift of 7. Now that drop is real, but by going at higher redshifts, when the universe becomes more neutral, we would have expected to see nothing in the Lyman alpha spectrum of galaxies. 2014, so way pre-JWST, there was this publication, strong Lyman alpha emitter at redshift 7.5, and this came as a surprise to me because it was a higher redshift than I would really have expected to see strong Lyman alpha emitters. And the field just sat here for about a decade until JWST turned on. And within the first 3 months, delivered a Lyman alpha emitting galaxy at redshift of almost 11. This, I think, is a legitimate surprise. We expect the universe to be more than 90% neutral at this time. And not only that, but later part of last year, this redshift 13 Lyman alpha emitting galaxy was also published. And now I give up trying to predict when you don't see Lyman alpha anymore. All bets are off. You can see Lyman alpha emitters wherever you like in the universe. And these are the things that really put this talk into context. This is the stuff that I'm interested in trying to figure out about our early universe. We want to know what the conditions in the average galaxy are. And so if you want to know the conditions in the average galaxy, you have to observe a heck of a lot of galaxies. These are a heck of a lot of galaxies, even though it only looks like 5. These are the stacks of about 1,000 galaxies seen with JWST spectroscopy at redshift between 5 and 10. The average, no, 4.5 and 10. The average redshift is about 5.5. And these spectra that you see here, you see the optical spectra, 3,000 to 7,000 angstroms on the right, and this is the UV Lyman alpha going down to about 2,500 angstroms. What you're looking at here is stacks of about 200 galaxies contributing to each of these lines, equating to about 2 million seconds of integration time per pixel. And of course, I ordered these. The details of the ordering don't matter, but what you see in the blue, the darker blue colors here are galaxies that are less star forming, going up to the galaxies in yellow here. The yellow, it's about 200 galaxies that are have very high specific star formation intensity. And you see many different things changing in these spectra. Of course, the emission lines are becoming stronger when you look at the the more star-forming galaxies. You see the emergence of this Balmer break associated with the age of these stellar populations. You see the change in color in the ultraviolet continuum as the stellar populations get hotter towards the more star-forming galaxies. And what I think is really cool is that you see the emergence of these strong ultraviolet emission lines. These are the ones we use to understand the properties of the ISM, the abundances, look for evidence of black holes. It's these things that I'm really going to focus the first part of this talk upon. I'll talk first of all about, what we need to reionize the universe. So if you want to reionize the universe, you need to know the ionizing emissivity of galaxies. They need to be making and emitting. So making is one part, producing the ionizing radiation in the first place. They also need to be letting it get out and flood into the intergalactic medium to produce that ultraviolet background in the orange light in the simulations I showed at the beginning. So observers typically cast the first part of this as the ionizing photon production efficiency of galaxies. And this is something that we define a quantity that we call psi-ion, and it's the number of ionizing photons produced per second by a galaxy, normalized by the UV luminosity of that galaxy. And so 15-year-old calculations, we know what the hydrogen number density of the universe is, we know what redshift is, we know what the density is as a function of time. So you can compute pretty easily, actually, how many ionizing photons you need to keep the universe ionized. And so old calculations tell us that if you have about 10 to the 25.2 of these in this quantity of psi-ion, then you have a population of galaxies on average that's capable of reionizing our universe. Now, if you look at the numbers that we measure here, we can calculate Q0, or the ionizing photon production rate, really, because this is hydrogen Balmer series radiation. So every photon emitted in the H alpha, H beta spectra of galaxies was once an ionizing photon that got absorbed locally in the interstellar medium. So this is essentially just a counting experiment and conversion of photons into this quantity that we call psi-ion. These stacks, as I said, were ordered by specific star formation intensity, and you see them getting stronger and stronger until we have numbers up here, 10 to the 25.6 or so. And 25.2 is what we need. So this is 0.4 dex, more than a factor of 3 more photons in the budget that we can use to reionize our universe. So these populations of galaxies in redshift 6 or so, no problems. No problems with the budget, at least. What matters on top of that, of course, is every one of those hydrogen Balmer series lines that we just saw, that's it. Everything okay? I guess. Yeah. It's been 17 minutes. Oh no, I apologize. I know that I should have. Oh yeah, you're absolutely right. Where is the Zoom? The Zoom is here, right? So then I have to share, is it?
Yeah. Okay.
Share, and then I share. But that's the wrong one, isn't it? Don't I have to share?
I think.
If I share this?
Yeah.
It's then gonna.
And then you go to your screen. Yeah, we see this.
We see it, okay. And then what do? I go to the what's it? To the PowerPoint? No.
Just go there.
Oh, I did it by pressing that little thingy button down there. That's how I did it. This one. Where's the mouse? Mouse is here.
It's here.
Okay, I went there. That's how I did it before.
Sorry.
Oh, I'm really sorry about that. Probably there was an instruction that I should have followed. Yeah. All right. So, okay. Where were we? What matters is the fraction of ionizing radiation that escapes from these galaxies. Like we have enough photons, we have to make sure they get out. And this is something that you can't observe in the reionization epoch, almost by definition. Well, by definition, right? Because the universe is neutral, the universe is being reionized, all of the ionizing radiation is absorbed locally in the intergalactic medium doing that reionization. So we can never measure that flux by construction in those galaxies embedded in the. And it's even worse than that, actually. The IgM becomes so thick, even in the Lyman alpha forest at redshift beyond 4 or so, that you can't measure the ionizing flux from galaxies out there. And this leads us to the local universe and sort of what Daniel was saying in his introduction, that we spent a lot of time working on local analog star-forming galaxies for exactly this reason, that we need to be able to understand the properties of how galaxies emit their ionizing radiation. And this is sort of the leading survey of this, the low redshift Lyman continuum survey. Both Hakeem and I are involved in this. And you take spectra, you take hundreds of orbits of HST data, measure a sample of about 100 galaxies, trying to measure their Lyman continuum, their ionizing radiation output over here. And then what we do is really a big correlation experiment, where we sort of, estimate the fraction of ionizing radiation escapes, this we call the escape fraction, correlate that with other observables that you can see at basically any point in the universe. So this is just a correlation between Lyman continuum escape fraction and UV color. This is the same number on what escape fraction correlated against the opacity of the ISM, or actually the inverse opacity of the ISM. And you can see that there are correlations on these figures, but there's an awful lot of scatter. Right? Now you can wonder whether that's, to what extent relations with that much scatter are useful. Here's the best thing we can do with multi-parametric regression techniques. We can sort of predict the escape fraction of galaxies versus what we observe from other way around. We can predict the escape fraction of ionizing radiation from other observables and correlate that with what we actually know it to be. We can do a pretty good job. We can explain half of the dispersion with a remaining residual dispersion of about 0.3 dex, factor of 2. It's all right. Seen worse. And then we can use these. We can go and apply these scaling relations between the escape fraction and other observables with things that we see or we can measure in the same stack spectra. I did the same stacks before. This is UV color. Now we're just looking at the strength of emission lines. We can see that again, I've sort of color-coded these diagrams by galaxies that don't emit their ionizing radiation and those that do. And our highest star-forming, the spectra of the stacks of our most intensely star-forming galaxies start to push into this range of significant escape fractions for about the upper 50% of galaxies. They're median stacks, and the middle stack is right on the line. So you can say that, on average, up 50% of this galaxy population is getting into the region where it emits a substantial amount of ionizing photons. And you can do this with many different observables. But it looks like that a decent fraction, half of the galaxies could have escape fractions that are what we need in order to reionize the universe. And this is good, especially since our budget, our photon budget, cast as the ionizing photon efficiency, is pretty high. And this is good. So we have enough ionizing photons probably to ionize the universe. I don't think this is a problem. We were worried about this 5 years ago, and I don't think it's the biggest concern that we have to face right now. Another thing that we see in these nice spectra is these strong nitrogen lines, and that tells us about the abundance of nitrogen. There's also carbon, oxygen in these spectra, so we can look at the abundances of nitrogen, carbon, and oxygen, compare them with each other. This is what I talked about in the introductory slide. There were a handful of galaxies identified in the first couple of years of JWST data where the inferred nitrogen abundance, and I say the inferred nitrogen abundance because I think there's a handful of other explanations that can also come in here. But if you look at what we would guess the nitrogen-oxygen abundance ratio to be, it seems to be elevated in many of these in some of these star-forming galaxies in the early universe. And there's been many explanations for how these strong emission lines could have come about. It sort of reminds me of the early days of gamma ray bursts, when people used to joke that there were more explanations for the GRBs than there were actual events. This started about that way, that there are about as many explanations for the enhanced nitrogen lines as there were strong nitrogen-emitting galaxies. And there are about 7 of these things known, and we're not far off. There's many explanations that there are. But it could be related to as well as enhanced nitrogen abundances, you have to explain where that comes from. Does it come from a population of extremely massive stars, or different stellar evolution that's going on, or the fact that these stars are forming potentially in very dense environments? Very dense environments not only could change the stellar evolution, but could actually retain the nitrogen gas inside star clusters, so you actually measure more of it and the emission lines become stronger. It could be connected with the AGN phenomena, and there have also been ideas that even tidal disruption events could cause this small number of galaxy emission. But this you can measure in the stacks that I told you about. And these stacks now, again, each one of these is the average, the median average of about 200 galaxies. And we still see these strong nitrogen lines, but they're not as strong as they are in the extreme galaxies that have been published. In fact, I admit that the error bars on this in this diagram are pretty significant, but they tend to fall on average in between the population of low redshift galaxies and the population of high redshift galaxies. So whatever process it is that's leading to these enhanced nitrogen lines, it's not just happening in the 7 galaxies that have been compiled in various papers. It's happening in every galaxy at some lower level. It's just, and we still don't, this data itself doesn't point us in that direction, except, well, if the AGN interpretation is accurate, that would imply that there are AGN present in, if the median stack, so more than 50% then, of the galaxy population that enter these stacks. That's possible. It's a subset of the galaxy population after all, but it is quite a high number, or not what you would expect for a typical AGN occupation based upon other metrics. Certainly, if we're preferentially selecting galaxies that are forming very dense, very compact star clusters, these are certainly the points where you form the most massive stars in the universe and the low metallicity. This could be certainly you have to retain this gas, keep this gas very dense. It could certainly be connected to the population of massive stars that you would expect in star clusters. So these two possibilities look quite likely. And in the average galaxy, I think transient phenomena are almost certainly going to be ruled out. If we look, but the nice thing about looking at dense environments is that they're also the sites where you would expect under most of the formation mechanisms the first black hole seeds to have been planted. And these are manifest in many observables in these spectra. This is just a zoom in on the UV emission lines on about half of the galaxy sample. Now you have these strong emission lines that give carbon, helium-2. Helium plus emission, or helium-2 recombination lines are strong in these spectra. And for this, you need to have 54 electron volts to ionized gas. But that's not easy to do with stellar populations, and this can be AGN diagnostics. The nitrogen lines I've already talked about could be interpreted as signatures of AGN. There's a strong magnesium-2 feature up here, and what I think is actually really cool that we haven't done much with yet is the presence of this quintuplet carbon-2 at 23, 25 angstroms over here, which is never seen in star-forming galaxies in the local universe. Not saying this is coupled directly to the AGN phenomenon, but it's very interesting. And if we put these, we can use the ratios of these emission lines to test whether the population, whatever is doing the ionization in these galaxies is connected to stars or AGN, using diagnostic diagrams that look like this. And there's many of these that have come out in the last couple of years. Here we're looking at the equivalent width of carbon-3 versus a line ratio of UV lines. It doesn't really matter. What's important is that the AGN should fall up here in this gray region of the diagram. And I think that these equivalent width-based diagnostics are actually really powerful because that's really connected with the number of ionizing photons that whatever this ionizing source is producing. And this is really something that where AGN and star formation is very different because you have power law versus exponential ionizing continuum. And so, for the most intensely, what I would have thought were the most intensely star-forming galaxies in this population, they're sitting up here on the border between the star formation and AGN activity sort of region. Now, it's not all diagnostics that place them there. If you look at the some photoionization and shock models here, actually produced both by 2 IAP alumni, 10 years ago or so, it seems like they're sort of dropping more into the star formation dominated region. But these line by line diagrams are the parameter space explored by these models is probably not that broad. And these could overlap more than we expect. But if you take this diagram at face value, it would tell you that half of the galaxies in 40% of the galaxies equals 20% of the galaxies could have a contribution of AGN ionization to their spectra. And that's, I think, it's not a unique interpretation, but I think it's very interesting in light of where we're going to go next. Because another thing that we need for our galaxy formation theory is a decent understanding of where the first black holes have come from, because we need to know how to insert them into our models of galaxy formation. And if you look at some of the biggest simulations, you take, for example, the illustrious. I don't want to pick on illustrious, but they're all doing basically the same thing in one way or another. Is you let the dark matter halos of galaxies grow just by assembly under gravity. And when they reach a certain threshold mass, you just drop a black hole into the center of the galaxy. And that leads to a number density of black holes that starts off very low, of course. And as galaxy halos assemble, get more and more massive, the number density of supermassive black holes increases, and with that, the AGN phenomena should turn on. And there are other ways you can refine this, looking at have different criteria. But the bottom line is that all of these prescriptions are actually that. They're prescriptions. They're not physically motivated models. They're ways of inserting black holes. And as I said in the very beginning, these galaxy formation simulations are really, really good at reproducing the galaxy population. So why do they work so well? I mean, what we would like to be able to do is replace this with a physical model for how black holes are formed. And this is an area that's not new. This is a rather complicated way of route to making black holes out of a gas cloud, which has been obscured by Zumba. But they boil down roughly into three families of black hole formation scenario. One in which you form these dense stellar clusters that I've been talking about tangentially throughout the talk. You have very dense environments. You have very fluffy stars. They sink to the center. You can have merging stars. You can ultimately produce relatively massive seeds on the order of 10 to the 3, maybe 10 to the 4 solar masses. We still refer to this as sort of lightish seeds, but you can form black holes in this way in principle. The other way is that they form directly by the collapse of massive stars, probably population 3 stars, very low metallicity objects. Here you're talking, of course, about black holes that form at approximately the masses of stars, up to maybe 100 solar masses. If you introduce some exotic physics here, you can actually push these up to much higher stellar masses, but it's all based upon the ideas of stellar evolution that have never been observed. And the third way of making black holes, at least astrophysical way of making black holes, is through a process that we call direct collapse. So you have these dark matter halos, atomically cooled halos. You prevent them from forming any molecules, so you keep the cooling really, really, really slow, and you end up with very smooth density profiles that shift into the central regions of the dark matter halos. And you can produce massive seeds by what we call direct collapse in these halos, giving us sort of 10 to the 5 solar mass seeds. These are very rare, or very rare even in simulations. We don't know if it happens at all in reality. And the other sort of way this becomes other route to observational diagnostics is that we need to be able to have black holes at the mass that we find for quasars at redshifts of about 7 or something like this, where we know that there are very massive black holes at redshift 7. We need to be able to grow them to be that massive by that time. You don't have very much time in the universe, and so if you just plot back their masses, assuming that they grow at the Eddington rate, then it already tells you that maybe you have to form some black holes already through this route of direct collapse, or you have to grow them very fast, or maybe the masses aren't quite what they're estimated to be. But it is tough. It is tough to get these massive black holes in place by redshift 7. And then there's, of course, the scaling relations. We have to make sure that the black holes are not too massive for their host galaxies. And we also have to have a seeding scenario that's able to make enough black holes per unit volume. So we not only do we have to form some of them perhaps very massive or grow them very quickly, but we have to have a mechanism that makes enough of them. And so our contribution to this, or a project that we've been doing in Stockholm, is an effort to estimate the number density of black holes that we see at redshift beyond 6. And we've been using the technique of photometric variability to do this. So one of the nice things about, there's many awesome things we've said about the JWST telescope, first of all. But what it doesn't have, being new, is a 15-year history of observations like HST does. So HST first visited the ultra-deep field, actually in 2006, but in the infrared in 2009, where 150 hours are put into just imaging in like 3 filters, producing extremely deep images in a patch of the universe. And this was revisited 3 years later, 2012, but some of the same filters were observed, adding a new one. And then we waited 11 years before adding a new filter, a new epoch to the Hubble Ultra Deep Field imaging in 2023. We tried to do it several years before that, but the panel wasn't particularly receptive to our efforts. But we're doing this in the UDF, Hubble Ultra Deep Field, where there's 27 bands, I think, of HST and JWST photometry, some of it from multiple epochs. It's to have the best photometric redshifts and spectroscopic redshifts effectively anywhere on the sky. And we're looking for variable sources in this field. So variable sources, because the accretion rate of matter onto the black hole can change, AGN can vary on short time scales. And so looking at photometric variability is a nice technique to look for AGN, particularly at faint magnitudes, and also because it's, the spectroscopic methods are very good, absolutely, but you have to decide which galaxies to go and take spectra of. Whereas if you just re-image fields again and again, you're looking for variability. You can look for AGN activity in basically every source in the field. And here's an example of one that we found is very variable. These are subtracted images. It's a redshift of 3.2. And we confirm this is an AGN with JWST spectroscopy. We see there's broad lines. But redshift 3 isn't really what we're talking about, what we're interested in. At redshift 6, we do the same for everything in the field. We don't even know what redshift it's at. But we do find variability in sources that lie beyond redshifts of 6. Here's an example of two subtracted images, a source that's getting brighter and then fainter again between 2009 to 12 to 23. We actually find 3 sources beyond redshift 6 that are doing this. And you see in this sort of pseudo light curve here, if you have any sort of transient astronomers, supernova astronomers here or whatever, talk about the term light curve. This is technically a light curve. It just has 3 data points on it. And you see a source that gets brighter and then fainter. Now, the important thing about these long time baselines that go over 15 years is we have to account also for cosmological time dilation, this factor of 1 plus z. That means 15 years in the observer frame is only 2 years in the rest frame at redshift of 7 or so. And there are no stellar transients that we know of that move on light curves that are so long. And so this is almost certainly, this is a resolved source. There's fuzz up there. It's not point source, so it's not galactic. And this is how we go about finding AGN in the early universe. We find 3 of these between redshift 6 or 7. That gives us a volume density, admittedly one that's subject to low number statistics in the Poisson regime. But if we calculate the volume density just of variable sources, we end up with a co-moving number density down here. This little red dot here is the number density of little red dots, if you've heard of those. I recently discovered AGN population at high redshifts. This variability analysis sort of gives us slightly higher number density, but we know that all AGN 10. All right, 10. Really? All right, okay. And we know that they, now I'm distracted. We know that not all AGN are variable, but we do have an idea what the fraction of AGN that are variable is, because we can even calibrate it in this kind of multi-epoch imaging data against catalogs of known AGN. And we know that about, a quarter to fifth, 20-25% of AGN seem to be variable in the catalogs that we're working with at the depth that we are working with. And that allows us to make one upwards correction. And so, what we're seeing with photometric variability is number densities that are comparable with those that have been derived by broadline spectroscopy. And again, we know that this isn't the complete population of active galactic nuclei out there. There's other forms of AGN. And there's also, of course, a population of black holes that isn't accreting right now at all. And so we can actually believe that the number density of black holes may be all the way up here, stating that perhaps at the magnitudes that we're sensitive to, maybe one galaxy in 20 or so is actually occupied by a massive black hole. Now, if I have 10 minutes, I'm going to skip what we do about this, but we have modeled these variable sources with a new population SPS with a code to model stellar populations and try to estimate their masses. These are our mass black hole stellar mass relationship from our variable sources. The red sources here are the high redshift sources. We're also finding black holes that may be overmassive, but we can talk about it at another point, because I do want to spend my remaining 10 or 12 minutes talking about the effect of these galaxies and AGN on the intergalactic medium. So I asked one of these generative AI tools, I can't remember what it was called, I probably written a little citation, to generate me an image of a galaxy in an ionized bubble and the Lyman alpha emission line, or so I can't remember exactly what the prompt was. It gave me this. I think it's interesting. It says Lyman ultra, which I kind of like. And you know what these tools are prone to doing, this looks to me very much like a hallucination in more ways than one. Sorry?
Okay, or something, she's solving.
Ah, yeah, it's been there for a while. Oh, yeah, I think I have to okay that. It's up behind you, Danielle. It's on the right screen. I can okay that. Voila.
The other one.
Maybe I could even cross that one off as well. Oh, look at that. I should have done that like some minutes ago as well. Ah, technology. Anyway, so then this looks like I was gearing up to my joke about this looking like a hallucination in more ways than one. And then it fell flat. And now I can't change slides. Why can't I change slides? That'll do. I guess I have to do that. And I said before in the introduction that Lyman alpha is the strongest spectral line intrinsically in the spectrum of ionized galaxies, and also ionizing galaxies, also AGN, and that it comes from the radiative electronic cascade of the hydrogen atom in recombination nebulae, is produced by this n equals 2 to n equals 1 electronic decay. And because of this, because of the fact that galaxies contain a lot of atomic hydrogen, this Lyman alpha gets immediately absorbed, scatters, and it becomes a complicated radiative transport problem. And that's why spectra look the way they do. They look to be broadened. There's blue and red peaks because you just can't shift the Lyman, you can't get the Lyman alpha to transfer through atomic gas. If you look at a spectrum of a local strong Lyman alpha emitting galaxy, this is a beautiful image produced where we observe the H1 directly with the Meerkat array. And all the H1 has been stripped out of this galaxy. And that's probably a big reason why this galaxy is a strong Lyman alpha emitter, because all the atomic gas, or the bulk of the atomic gas, has been ripped out. And that's, that happens in the galaxy. That gas can be in the galaxy, it can be in the circumgalactic medium, or it could be in the intergalactic medium. It doesn't really matter, provided the H1 is close to the galaxy. And then if the H1 is close to the galaxy, or you put a galaxy in a neutral universe, what you should expect, these spectra have all been observed redshift 0.2, 0.3, where the IgM is fully ionized, so you can see all the Lyman alpha perfectly well. If you were to put these galaxies in a neutral universe, it's just like closing the curtains on them. The Lyman alpha should go effectively to 0. And this gives us what is a pretty powerful tool to investigate the reionization history of our universe. Because this absorption of Lyman alpha spectra near the Lyman alpha resonance is absolutely nothing new. This is something called the Gunn-Peterson trough that we've known should exist since the 1960s. If you put some galaxies into a neutral IgM, the Lyman series of Lyman alpha absorption should produce this strong absorption going out to more than 1250 angstroms, killing any Lyman alpha that's there. So if you put your Lyman alpha emitting galaxy in a neutral universe, you should end up with a spectrum that looks a bit like this. But if you put that galaxy instead into a big ionized bubble, the Lyman alpha will then escape from the galaxy. And it will start transferring until it meets this edge where the universe becomes neutral. Now, if that bubble is big enough, you just need the universe to expand a little bit to give you a couple of angstroms of redshift on the Lyman alpha line. It escapes resonant absorption with the hydrogen, and then it's free to transfer to as far as it wants to Earth. And though the size of these ionized bubbles is then going to be important for the observability of Lyman alpha in the early universe, and that's probably why, must be why, we can actually see this emission from that redshift 13 galaxy. So this is the cartoon diagram here. This is what I wanted the generative AI to improve, to give me a nicer version of this, but it didn't. So I have to use the cartoon version. Anyway, this drop of this absorption of Lyman alpha manifests in various different ways. There's many sort of observational diagnostics we can use here, but you can imagine sort of intuitively, right, that if you start to look at the Lyman alpha luminosity function, which is just a number of the Lyman alpha number of galaxies at fixed Lyman alpha luminosity, as you look further back into the reionization epoch, it should decline and decline. So that's one observational diagnostic that we have. But there's also this sort of spectral shape here that we know is sort of this intrinsically this sort of double peaked emission line, a weak blue part and a strong red part. And if you put this spectrum into an ionized bubble, it will absorb sort of according to the Voigt profile, offset by some wavelength that we implement as a velocity, but is really just the size of the ionized bubble. So you can use the shape of these Lyman alpha emission lines to estimate the size of the region, the ionized region in which a galaxy may lie. And here are just some examples of how that may look for different redshifts. This is a sort of a simulation of the same intrinsic spectrum always at redshift 6 inside a bubble that corresponds to a certain redshift. You see the blue side is all killed, and then the red side is both shifted a little bit to the red and suppressed by the damping wing. You do the same thing at redshift 10. The neutral gas in the IgM basically kills all the Lyman alpha. But if you put that inside also redshift 10, inside a big bubble, you can still end up with a significant amount of Lyman alpha transferred. So we built a model to try and explain this, or try and estimate the size of these ionized bubbles in which the observed Lyman alpha galaxies seen by JWST and other ground-based telescopes have been, must be residing. Here is the size of the bubbles that we infer on the, I haven't updated this slide. Okay, here is the size of the bubbles that we measure in a sample of about 35. Here it says 25, it shouldn't be 35, it should be 36 data points on this plot. This is bubble radius in physical megaparsecs versus redshift for a sample of 36 galaxies seen with JWST. And what we see here is galaxies in the very early, redshift beyond 10 of these two examples over here, they seem to reside in rather small bubbles. And by the time you get to redshift 7 or so, well, still some galaxies reside in rather small bubbles, but you see a distribution here shifting up towards, sizes beyond 2 up to 3 megaparsecs, according to the inference here. And this is quite important because it's exactly what we expect, exactly how we expect ionized bubbles to grow during the reionization epoch, right? They start off as small bubbles around little galaxies, and as the time goes on, we have not only more time to ionize, but the more galaxies turn on and bubbles grow and grow. And this is the first time this has been actually observed in astronomical data. What you see here in the gray band are expectations from cosmological radiative transport simulation. And this is exactly the sort of kind of data sets that we need to constrain the different models of reionization done in simulations like this. I suppose we're basically out of time. I wanted to say one more thing about the luminosity function that I'm not going to do. I will just leave up my summary slide. It says 47 minutes. So we can end there, and we can talk about any aspects of this that you would like.
Thank you, Matt. Very stimulating presentation. A lot of talks.
There are many things in there, but I want to try and do something broad.
But you mentioned AGL all the time. AGM.
IgM, yes.
Or ISM from the galaxy you're talking about. It's not the same thing.
It's not the same thing. I mean, what we want, there's many ways we can infer the properties of the interstellar medium. Lyman alpha is probably not the best one, given the other wealth of emission lines that we have to look at the ISM. There are things, I guess, you can learn about ISM with Lyman alpha, column densities, things like this. Winds, exactly, yes, exactly. I mean, the reason why, yep, exactly as you say, the reason why the intrinsic profiles are asymmetric is because the blue, you put this in a static medium, those two peaks would be the same height. If you blow the gas out, the blue one gets suppressed, and that's why the red one is stronger than the blue one. That's absolutely to do with the kinematics, and encoded in there somehow with the outflow velocity, absolutely. This was your big 1998 paper, I recall. Well, Yes, but what I think that the main diagnostic power of this Lyman alpha emission line is really in figuring out what's going on in the IGM. Because here, there are ways we can do this. Ionization, reionization history you can look at with cosmic microwave background, and you can get one data point. You can look at it with quasars, and then there's some things you can do, but typically you're really looking at the very last stages of reionization with quasars. So redshifts 6.5, 7.5 on that damping wing of quasars. And then if you want to go further than that, it's galaxies. And the nice thing about galaxies is that we can see them out to redshift of whatever the answer is, 16 or something. And in principle, then, we can use these galaxies not only to give us one estimate of the column, but to actually start to figure out what the bubble size distribution, what the ionization fraction is as a function of time. And I think that's really the power of Lyman alpha galaxies, and not much more that you can do that with.
Yeah.
So, I have a question about the nitrogen emitters.
Yes.
Okay. So as you said, one of the possibilities may be massive star clusters. Okay.
Well, the massive stars that you form in, okay, so this is, and just sort of, I think in two ways, the idea, okay, so star clusters are great because they're a very good way of bringing stars very close to other stars. And this could be very important in the, particularly for the very dense objects that we expect to form in the first populations of galaxies. Also, when you're forming very low metallicity stars that can tend to be very fluffy in the outskirts, you can then, not only do they sink very rapidly to the bottom of the potentials, but they also have the possibility of stellar mergers. And so this is a way that we could make extremely massive stars, which not only is a very good black hole seed, but could also change the stellar evolution in such a way that we end up with larger production of nitrogen. Now, the other important thing about the clusters is that deep potential, because all of this material is blown off the stars in winds. And deep in the center of the most dense star clusters, you have a potential that can probably retain more of that nitrogen. So not only could it be overproduced, or maybe not necessarily, it may or may not be overproduced, but you also have potentials that retain it and make it, drive up the strength of the nitrogen lines in the observations. So that's why I like star clusters. But, oh, I'm sorry. Okay.
They live for 10 million years.
Or less, yes. Yeah.
So we think back in have less time than that.
Mhm.
The most massive stars come very close to the supernova.
Mhm.
So whatever they do, when they become supernova, they inject oxygen.
Mm-hmm.
So the nitrogen and the oxygen goes down, not up. Which means that in practice, you have just a couple of million years.
Yeah, okay, so the point is that nitrogen and oxygen are both produced in the core collapse, but with oxygen more, but then you have to wait for secondary nitrogen to come on the AGB. So, yeah. Yeah, I know. Yeah, yes.
So how long they live there?
Well, not a direct. Well, yes. Okay, so I can estimate ages in these stacked spectra in a couple of ways. If you look at the equivalent widths of some of the Balmer lines like H beta, you can get a constraint on the age of the stellar population. And also we've been doing some modeling of the stellar spectra themselves with population synthesis models. I can see, if I just look at these now, you see, for example, in some of these cases, the more evolved galaxies, the blue ones down here, you see the presence of a Balmer break, and it's these kind of techniques that we can use. This orange one here even has a Balmer jump, an inverted break. So we can use these stellar spectra to estimate the ages. I do have them in the paper. I can't remember what they are, and I don't have a backup slide on it, but I can tell you afterwards. If you look at the strength of these emission lines, where's H beta? H beta is there. It also gives you an independent constraint on the age of the stellar population. If you look at I don't have exactly the right number, but these these spectra are stacked in order of increasing oxygen 3 equivalent width. And in the yellow spectrum here, that they are all in excess of 1,500 angstroms in equivalent width. And that means, you know, a lot of them would even be much higher than that. This is the median value. So while I can't immediately translate that into ages to produce equivalent widths like that for an instantaneous burst of star formation is, yeah, 3, 4, 5 million years. Yeah, sure. Joe had a question. He's figured it out. Oh, well, okay.
Another question?
You mentioned in one of the scenarios for the formation of massive or supermassive black holes, you had 2 scenarios. If you so you mentioned post-Newtonian instability on the left. I was wondering what it is exactly.
Oh, so where do I mention post? What do I mention?
Just post-Newtonian instability.
On the
After a
right.
supermassive star formation.
Where is it? Guide me.
The left.
No,
Well,
yeah.
yes, right.
Yeah.
Yes.
You have to ask Martin Rees. I'm sorry. This is a paper. This is a figure from Martin Rees's 1984 review article outlining these different channels. It's so complicated. I don't know what post-Newtonian instability. You have to ask. I hadn't even read it, to be honest.
I have one. You showed the average 5.5 set of spectra just now. Yeah.
I was just up there. Where's a good one? It's on many slides, but this.
Then you deduce that you have enough photons to ionize the universe, etc. So, what did you work out, basically? What kind of assumption you have? Because you
Into that calculation. Sorry?
You have to know the neutron density, volume density.
Well, I think that's actually very easy. That, I mean, knowing the hydrogen density of the universe at redshift z is it's the, well, you know what the matter density is at redshift 0? You know how much of that matter is hydrogen. You know what the mass of the hydrogen atom is. So we know what the hydrogen density is at redshift 0. And the hydrogen density at redshift z is that number multiplied by 1 plus z to the 3rd power. And then you know what the volume density is. So if that gas is ionized, you know what the recombination rate is. You know how fast the universe recombines at any redshift. Assuming that there's no clumping, which there is. But you know what the recombination rate is. And for a sort of smooth universe, this is a quite simple differential equation. You need to have so many ionizing photons. You know what the photonization rate is. You know what the recombination rate is. You can work out how many, and you know that at what time the universe was fully ionized. You take that to be redshift 6. And then you have to know what the luminosity function is, and you can get the number of ionizing photons you need to make the universe ionized by time, whatever.
Now, the way to spell this, average spectra of 4 to 10 there.
Z equals 4 to 10, so 4 is low redshift bound.
Average spectra. You have observational value.
Oh, yeah. Oh, there. Oh, yeah. Oh, there's many. Yeah.
Knowing that.
Let's say that.
Bias already enough.
Yeah. So the observational bias. I mean, okay.
Not the average spectra.
No, you're right. It's not the spectrum of the average galaxy. And in fact, I would be quite. It's a frightening prospect to try and even figure out what that would, how you would go about knowing exactly that. Of course, this is so we have, by 18 months ago, JWST in this prism mode, low resolution spectroscopic mode with near spec, had obtained in excess of 1,000 spectra of galaxies in this redshift range. They come from a large number of programs, dozens of programs, 20, 30 different observational campaigns that all use different selection effects. They're all interested in galaxies at different epochs with different colors, different bumps in the photometric SEDs. They are assembled, could argue that if you use enough different approaches, you're sort of averaging over all of the selection effects. But yeah, it is absolutely fraught with selection effects. But this is a population that we know about. So the way to say it perhaps is the population that we know about produces enough ionizing photons to ionize the universe.
Yeah. Oh, no, no.
One of the possibilities is to have
Hmm? Yeah, so
And you will friends because of
So I mean, the question, it was, I can try and paraphrase. You want to know about the possibilities of growing black holes through mergers of intermediate. Well, okay, and we know that black holes do merge. You can make two intermediate mass black holes. Yeah, okay. To go from the intermediate mass regime of 10 to the 5 to the observed mass regimes above 10 to the 7, which is a pretty low mass for the observed mass regimes, means you have to merge together 100 intermediate mass black holes. And they're pretty small, right? So you have to find a way of bringing large numbers. I mean, they'll grow through accretion. Of course, black hole merge. Yeah, black holes merge. It takes a Hubble time to see a handful of black hole mergers. I mean, we know that. I don't know how to answer the question really. It's hard to formulate the I don't know where to go. Absolutely, black holes merge. I doubt it's a way of making significantly more massive black hole seeds, just because the sort of merger timescales are going to be extremely long. And even if you merge two, you've only doubled the mass.
yeah. Say that maybe you mentioned that, but I have not. I don't remember. You find many AGN, low luminosity there. I suppose.
Low, so, I mean, certainly far sub-quasar luminosity. Yes, yes.
Yeah.
These are
And,
they're
so
L star.
So what do they break the famous? You know, I don't know if you can answer to that, but mass of bulge versus mass of other.
So we don't know about the bulge masses, and even if there are bulges. So bulge formation seems to be a modern universe phenomenon, at least as far.
Of course, very.
Yeah. I mean, they're certainly more massive with respect to the stellar masses of, certainly is even a strong word there. Observationally, we infer the black hole masses that we see at redshifts 4 to be more massive with respect to their stellar mass of their hosts than we see in the local universe. Bulges, I don't even know if they are there. So if you refer to it as a relation, then I would say yes, they lie outside the local relations. So the black holes grew very fast, very early, perhaps at the expense of the growth of stellar mass. I don't know.
And
Mhm. Yeah, so that's actually something that I skipped over. Don't have the star formation rates. I don't have. But one thing, so with my PhD student in Stockholm, because we wanted to infer what we could about these variable AGN. So with PhD student in Stockholm, we tried to do a lot of SED modeling of these guys, because the reason we did this is because we wanted to look for AGN activity in the fainter galaxies, and they tend not to have a wealth of spectra in the archives. We wanted to take away that bias of photometric preselection and just look for possible activity everywhere. So we have very few spectra. So all we can infer via SED modeling. The great thing about this field is the many bands. Every one of those black data points on here is a photometric band on the SED. I think it's 27, 26 from Hubble and Webb, if you add them all up. And then we tried to do some SED modeling. We actually couldn't do it with off-the-shelf SED code, so we made our own. And what you see on the left here is we modeled them all with a pure stellar population, as you would typically do, and then we modeled them all with a stellar plus AGN contribution. The left, what you're seeing here is our redshift 3 variable guy. What the sort of the one we're using to make a lot of examples with. It's quite well fit by the stellar population. If you add another population of AGN and start AGN on top of that, the SED modeler prefers there to be a prefers the AGN basically to dominate all throughout the red, and with the stellar population kicking in only in the blue side. If you take our redshift 6 example, you can get some kind of an SED fit with the stellar population on the left. When you try and do a stellar plus AGN fit on the right, the stellar population isn't even on the plot anymore. It wants to have 100% AGN basically for this galaxy. So we can do this kind of experiment, and we probably have star formation rates in our tabular data of the output. We can do sort of black hole mass versus stellar mass. That's on this plot. These colored points on here are our black hole mass versus stellar mass relationship. I don't have star formation rates really available, but I guess we have them in a table. Could perhaps look into that. Could try and infer accretion rate from the, I don't know, the AGN luminosity, and then compute the SFRs. I would expect them to be very AGN dominated compared. The SFRs are going to be modest because they're pretty faint.
Okay, thank you. There is no more question. We thank you very much for this.
Thank you very much for the invitation. It's really great to be here.